Welcome to this coding problem walkthrough. In this session, we'll explore problem number 20, valid parentheses. This is a classic problem that tests your understanding of stacks and string manipulation. Let's dive in and solve it step by step. In this problem, we're tasked with determining whether a string of parentheses is valid. A string is considered valid if every opening parenthesis, like or, has a corresponding closing parenthesis of the same type, such as or. Additionally, these pairs must be properly nested and ordered. For example, an opening bracket like cannot be closed by or, and the brackets must follow the same sequence in which they were opened. The input is a string S containing only these 6 characters, and our goal is to return a Boolean value, true if the string is valid and false otherwise. This means that we need to carefully verify the structure of the string to ensure it meets all the rules of valid parentheses. Let's look at some examples to clarify the concept. In the first example, the input S is the string. Here, we have one opening parenthesis and one closing parenthesis. Since they form a valid pair, the result is true. In the second example, the input string is. This time, we have 3 pairs of parentheses, round brackets, square brackets, and curly braces. All of these pairs are correctly matched and appear in the right order, so the output is also true. Now, consider a case where the string is invalid. In the third example, the input string is. Here, the opening parenthesis does not match the closing parenthesis. Because the brackets are mismatched, the string fails the validation rules, and the output is false. Another invalid example is. Although all the brackets are eventually closed, the order of nesting is incorrect. The opens first but is closed after, which violates the proper nesting rule. As a result, this string is also invalid, and the output is false. Finally, let's look at a valid and properly structured example. In the string, the opening is correctly matched with, and the opening is correctly matched with. Furthermore, the brackets are properly nested, with the square brackets enclosed within the curly braces. Since all the validation rules are satisfied, the output is true for this string. To summarize, the constraints of the problem require us to process strings with lengths up to 10,000 characters, which means our solution must be efficient. Some key edge cases to consider include strings with unmatched opening brackets, mismatched pairs like, and early closing brackets like, where a closing parenthesis appears before any opening parenthesis. It's also important to ensure that the stack we use to track open brackets is empty at the end of processing, as any leftover brackets would indicate an invalid string. Keeping these constraints and edge cases in mind will help us design a robust solution for this problem. To begin solving the valid parentheses problem, one possible approach to consider is a brute force method. The intuition here is to directly match each pair of parentheses by iterating through the string and ensuring that every opening parenthesis has a corresponding closing parenthesis in the correct order. While this may seem reasonable at first glance, it quickly falls apart for complex cases, such as nested parentheses. For instance, a string like introduces complications because the naive approach struggles to handle the hierarchical structure. Additionally, this method involves nested loops, leading to a time complexity of n squared, making it computationally expensive and impractical for larger inputs. Hence, the brute force approach is not suitable for this problem. A far more effective solution is the stack-based approach, which is the optimal choice for this problem. The key idea is to use a stack to keep track of unmatched opening parentheses as we traverse the string. When we encounter a closing parenthesis, we check if it matches the top of the stack. If it does, we pop the stack, otherwise, the string is invalid. This method works so well because valid parentheses are inherently sequential and nested, which aligns perfectly with the last in first out nature of a stack. For instance, edge cases like improperly ordered parentheses, such as or, are naturally handled by this approach. The implementation is straightforward. We iterate through the string, push opening parentheses onto the stack, and for closing parentheses, verify and pop the stack if the match is valid. At the end, the stack must be empty to confirm that all parentheses were matched. This approach has a time complexity of n, due to the single traversal, and a space complexity of n, for the stack. Its efficiency and simplicity make it the ideal choice for this problem. Another alternative to consider is using counters to track unmatched opening parentheses. The idea here is to increment a counter for every opening parenthesis and decrement it for every closing parenthesis. While this approach is simple and has an O(n) time complexity with O(1) space usage, it falls short for nested cases where the order of parentheses matters. For example, strings like or cannot be validated correctly because this method does not account for the proper pairing and sequence of parentheses. Ultimately, while the counter-based method might seem space-efficient, it fails to ensure correctness in the scenarios that matter most. Consequently, the stack-based approach emerges as the superior solution. Its ability to directly address the nested and sequential structure of valid parentheses makes it both practical and robust. Although it requires O(n) space for the stack, this trade-off is necessary to handle all edge cases accurately. The stack-based solution stands out as the optimal strategy for solving the valid parentheses problem. It strikes an excellent balance between correctness, efficiency, and simplicity. By leveraging the last-in first-out property of a stack, it effectively handles all edge cases, including empty strings, mismatched parentheses, and complex nested structures. The approach is elegant, robust, and ensures that every possible scenario is accounted for. With a time complexity of O(n) and space complexity of O(n), it is both efficient and reliable, making it the clear choice for addressing this problem. To solve the problem of validating a string of parentheses, we need to ensure that every opening parenthesis has a corresponding closing parenthesis and that they are properly nested. To achieve this, we use a stack, which is a data structure that operates on a last-in, first-out principle. This means that the most recently added item is the first to be removed, which mirrors the behavior of nested parentheses. The first step is to initialize an empty stack to keep track of opening parentheses. Then, as we iterate through the string, whenever we encounter an opening parenthesis, we push it onto the stack. If we encounter a closing parenthesis, we check the stack. If the stack is empty, it means we have an unmatched closing parenthesis, so the string is invalid. If the stack is not empty, we pop the top of the stack, which represents the most recent unmatched opening parenthesis, and continue processing the string. After completing the traversal of the string, the final validation step involves checking the state of the stack. If the stack is empty, it means that all opening parentheses were matched and closed correctly, so we return true. If the stack is not empty, it indicates that there are unmatched opening parentheses remaining, and we return false. The stack ensures that opening parentheses are matched in reverse order of their appearance, which is essential for proper nesting. There are important edge cases to consider. For example, an empty string is valid because there are no unmatched parentheses. On the other hand, strings with only closing parentheses or only opening parentheses are invalid. Similarly, strings with mismatched or interleaved parentheses, like or, are also invalid. Using a stack is efficient because its operations, push and pop, run in constant time, and the overall string traversal gives us a linear time complexity. Now, let's analyze the algorithm's complexity. The time complexity is O(n), where n is the length of the input string, as each character is processed exactly once. The space complexity is O(n) as well, which represents the maximum number of unmatched opening parentheses that might be stored in the stack. To understand the algorithm better, let's walk through an example. Consider the input string. We start with an empty stack and process each character. First, we push onto the stack, then another. When we encounter, we pop the stack, matching one. Next, we push another, and pop it when we encounter another. Finally, we pop the last, for the last. At the end, the stack is empty, so the string is valid, and we return true. Now, for the input, we push 2 onto the stack and pop 1 when we encounter, but the stack is not empty at the end, so we return false. In the case of the input, after pushing 2 onto the stack and popping 1 for the single, we find that the stack still contains 1 unmatched when we finish processing the string. This means the string is invalid, so we return false. For the input, the situation is different. The first character is, and since the stack is empty, we immediately know there's an unmatched closing parenthesis, so we return false without needing to process further. Here's the implementation of the algorithm in Python. We define a function as _valid_ parentheses that takes the input string. Inside the function, we initialize an empty stack and iterate through each character of the string. If it's an opening parenthesis, we push it onto the stack. If it's a closing parenthesis, we first check if the stack is empty, and if so, return false. Otherwise, we pop the stack. When the loop completes, we return true if the stack is empty and false otherwise. To further optimize the algorithm, we can make use of an early exit strategy. As soon as we encounter an unmatched closing parenthesis, we return false immediately, which avoids unnecessary traversal of the rest of the string. This optimization reduces the computational overhead in cases where the input string is invalid early on. Additionally, the stack is designed to store only unmatched opening parentheses, which minimizes memory usage. By keeping the operation simple and efficient, the algorithm maintains a time complexity of O(n) and uses space proportional to the depth of unmatched opening parentheses, which ensures it performs well even for larger input strings. The provided solution validates a string of parentheses to determine if it is balanced or valid. Let's break down the code step by step. 1. Initialization. The isValid function is defined within a solution class. It takes one argument, s, which is the input string. A stack is initialized as an empty list to keep track of opening parentheses, and a mapping dictionary defines the relationships between closing parentheses, keys, and their corresponding opening parentheses, values. 2. Iterating through the string. The function loops through each character in the string s. If the character is a closing parenthesis, i.e., it is found in the mapping dictionary, we check the top of the stack. If the stack is empty, we use a dummy value, hashtag, to prevent errors during popping. Then, we compare the top element with the corresponding opening parenthesis from the mapping dictionary. If they do not match, the string is invalid, and the function returns false. If the character is an opening parenthesis, it is pushed onto the stack for future comparison. 3. Final validation. After processing all characters in the string, the function checks if the stack is empty. If the stack is empty, all parentheses were matched correctly, and the string is valid. Otherwise, unmatched opening parentheses remain in the stack, indicating an invalid string. The algorithm ensures correctness by leveraging the stack data structure to enforce proper nesting and order of parentheses. The time complexity is O(n), where n is the length of the string, as each character is processed once. The space complexity is O(n), in the worst case, when all characters are opening parentheses and are stored in the stack. This implementation handles edge cases such as an empty string, valid, since there are no unmatched parentheses, strings with only one type of parenthesis, and strings with mismatched or improperly nested parentheses. It is concise, efficient, and adheres to best practices for solving this problem. Here, we start by importing the necessary utilities, like stack and map, which are essential for our implementation. The isValid method takes a string s as input and uses a stack to track opening parentheses. We also define a mapping that pairs closing parentheses to their corresponding opening ones, making it easy to validate matches later. As we iterate through the characters of the string, we check if the current character is a closing parenthesis by looking it up in the mapping. If it is, we pop the top element from the stack, but if the stack is empty, we use a dummy value like the hash symbol to avoid errors. Then, we compare the popped element with the expected opening parenthesis from our mapping. If they don't match, it means the parentheses are not valid, and we return false. On the other hand, if the character is an opening parenthesis, we simply push it onto the stack to process later. After iterating through the string, the final check is to see if the stack is empty. An empty stack means that all opening parentheses had matching closing ones in the correct order, so we return true. If the stack is not empty, it indicates there were unmatched opening parentheses, and we return false. This ensures that the function correctly validates whether the input string contains balanced and valid parentheses. In this example, we are given the input string. Let's follow the steps to determine if the parentheses are valid. Initially, the string is assigned to s, and the stack is empty. The first character is an opening parenthesis. Since it's an opening bracket, we push it onto the stack, which now contains one element. The next character is a closing parenthesis. The algorithm checks if the stack is non-empty, which it is, and pops the top element, resulting in an empty stack. It then compares the popped element with the mapping of, which is also. Since they match, this pair of parentheses is balanced. At the end of the string, the stack is empty, meaning all parentheses have been matched correctly. Therefore, the result is true. Here, the input string is. We start with an empty stack. The first character is an opening parenthesis, so we push it onto the stack, which now contains. The next character is another opening parenthesis, so we push it as well, updating the stack to single quote. The following character is a closing parenthesis. The algorithm checks if the stack is non-empty, which it is, and pops the top element. It then compares this popped element with the mapping of, which is. Since they do not match, this indicates that the parentheses are not balanced. The algorithm does not need to process further, as the mismatch confirms the string is invalid. Hence, the result is false. Now, the input string is. Again, we start with an empty stack. The first character is an opening parenthesis, so we push it onto the stack, resulting in. The next character is another opening bracket, so we push it onto the stack as well, updating it to single quote. The third character is yet another opening bracket, and we push it onto the stack, which now becomes. The fourth character is a closing parenthesis. The algorithm pops the top element and compares it with the mapping of, which is also. Since they match, the stack is reduced to single quote. Moving on, the next character is a closing bracket. The algorithm pops the top element, compares it with the mapping of, which is also, and finds a match. The stack is now. The final character is a closing parenthesis. The algorithm pops the top element and compares it with the mapping of, which is also. Since they match, the stack becomes empty. At the end of the string, the stack being empty confirms that all parentheses have been matched correctly. Therefore, the result for this input is true. Here, we're analyzing the time complexity of the algorithm. The first step involves iterating through the string S, where each character is visited exactly once. If the length of the string is n, this iteration contributes a time complexity of O(n). Next, for each character, we either push it onto the stack or pop from the stack, depending on whether it's an opening or closing parenthesis. These stack operations, push and pop, are constant time operations, O(1). Since we process each character exactly once, the total number of stack operations is also linear, O(n). Combining these steps, the overall time complexity of the algorithm is O(n), as each character is processed in a single pass with constant time operations for each step. Now, let's look at the space complexity. The main factor here is the stack that stores opening parentheses. In the worst-case scenario, the string contains only opening parentheses, such as, so all n characters are pushed onto the stack. This makes the stack size grow to n, resulting in O(n) space usage. In the best case, the string is either empty or contains immediately matched parentheses, like. Here, the stack remains either empty or minimal, leading to O(1) space usage. Additionally, the mapping dictionary, which is used to store the mappings of closing to opening parentheses, is a fixed-size data structure with just 3 key-value pairs. This contributes constant space, O(1). Overall, in the worst case, the stack space usage dominates, giving us an overall space complexity of O(n). To understand the algorithm's performance better, we can analyze it across different cases. In the best-case scenario, the input is either an empty string or consists of perfectly balanced parentheses, such as, or. Here, the stack is barely used, and the algorithm processes each character exactly once, resulting in O(n) time complexity and O(1) space complexity. In the average case, the input contains a mix of parentheses with some nesting and mismatches. The stack grows and shrinks dynamically as needed, but its size remains proportional to the input length. Time complexity remains O(n), and space complexity becomes O(n) due to the stack usage. In the worst case, the input contains only opening parentheses, like, or deeply nested valid parentheses. The stack reaches its maximum size of n, and all characters are processed. Both time and space complexities are O(n) in this case. To highlight the efficiency of the stack-based approach, let's compare it with a naive or brute force method. A brute force approach might involve repeatedly scanning the string for matching pairs of parentheses and removing them. This would require multiple passes over the string, leading to a time complexity of O(n², for a string of length n due to repeated scans and modifications. In contrast, the stack-based approach solves the problem in a single traversal of the string, resulting in O(n) time complexity. This makes it significantly more efficient, especially for larger inputs. Additionally, the stack-based solution is optimal because it uses space proportional to the maximum depth of nested parentheses, which is the minimum space required to solve the problem under these constraints. Finally, let's provide a mathematical proof for the big O complexity of the algorithm. For time complexity, we note that the loop iterates over the string n times, where n is the length of the string. Each iteration involves performing constant time operations, such as push or pop, which gives a total time complexity of O(n). For space complexity, in the worst case, all n characters are pushed onto the stack, requiring O(n) space. The dictionary used for parentheses mappings is fixed in size, contributing O(1) space. Adding these together, the total space complexity is O(n). In conclusion, the stack-based approach achieves optimal time and space complexities of O(n), making it highly efficient and well-suited for solving this problem. When working on problems involving parentheses, there are several common mistakes to watch out for. First, edge cases like empty strings or single characters are often overlooked. For instance, in a parenthesis matching problem, an empty input should return true since there's nothing to match, but a single character, like an unmatched opening parenthesis, should return false. These boundary conditions can trip you up if not handled explicitly. Next, stack operations are a frequent source of errors. If you try to pop from an empty stack, you'll encounter runtime issues. To avoid this, always ensure the stack isn't empty before performing a pop operation. Another pitfall is ignoring the importance of order in constraints. When handling sequences, the most recent unmatched opening parenthesis must be paired with its corresponding closing parenthesis. Failing to respect this order can lead to incorrect results. Finally, overcomplicating your solution is another trap. Problems like these are meant to be solved with simple tools like stacks or counters. Trying to use recursion or unnecessarily nested loops can make your solution harder to implement and debug, so focus on simplicity and clarity. Now, let's address input validation. It's crucial to ensure your solution can handle unexpected or invalid inputs, such as non-parenthesis characters or mixed data types. Ignoring input validation could lead to undefined behavior or incorrect outputs, so always check inputs before processing. Moving on to interview strategies, pattern recognition is a key skill to develop. Problems involving parentheses, brackets, or similar structures often follow predictable patterns of opening and closing, which can be efficiently solved using stacks, counters, or simple traversal methods. Additionally, while brute force solutions might technically work, interviewers typically expect an optimized approach. For parentheses problems, the ideal solution operates in O(n) time and O(n) space. Another critical tip is to clearly explain your thought process before diving into the code. Articulate how you plan to handle edge cases, satisfy constraints, and why your approach is efficient. Finally, practice is essential. Parentheses problems are just one example of broader stack-based problems. By solving variations like bracket matching or sequence validation, you'll strengthen your ability to recognize and apply these techniques in different contexts. Let's explore some related problems and alternative approaches to handling parentheses. There are several LeetCode problems that build on the same principles, such as valid parentheses, generate parentheses, longest valid parentheses, remove invalid parentheses, and check if word is valid after substitutions. These problems test different aspects of your understanding, from matching pairs to generating combinations or validating complex sequences. Now, when it comes to approaches, using a stack is often the go-to method for parentheses problems. Stacks are straightforward to implement and work efficiently for matching pairs, but they do require additional space proportional to the input size, or O(n). Alternatively, for simpler problems that only require checking balance without strict matching, counters can be a great option. They're more space efficient, using only O(1) space, but they lack the versatility of stacks in tracking the order of pairs. Lastly, recursion can be an effective approach for generating combinations, like in generate parentheses. However, recursion introduces trade-offs such as higher function call overhead and potential stack depth limitations, which can impact performance. Each method has its strengths and weaknesses, so it's important to choose the right one based on the problem's requirements. Great job! To summarize, we used a stack-based approach to solve the valid parentheses problem efficiently. Remember, mastering data structures like stacks is key to handling similar problems. Thank you for watching, and don't forget to practice and stay curious. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!